Okay, so I am live. If you are watching this VOD, video on demand, you know what to do. Skip a few minutes ahead to when I actually get started. I need to, first of all, get people to, on the live stream, say, yes, I can hear you, I can see you. So far, that's never failed, but I want to make sure that's the case. So jump a few minutes ahead, and I'll see you there. The topic is going to be riveted. So, okay. Just started the live stream. We have one concurrent viewer. And I say this every fucking day. Concurrent means you are watching. If you are that person, if you are watching this right now, you are the only person watching this, at least as of this moment. And I need something from you. You need to chat. Can you hear me? Can you see me? And is everything synced up? Because I'm not starting until that is the case. So, sheesh. If you are watching, you're now actually one of 6 people. Let me know, and then we can get started. I'm just going to set this super chat goal, because who doesn't like money? Let's see. So 3 hours. I will blink. Start goal. Okay, everybody can hear me. Everybody can see me. Amazing. So, here's the situation, boys. So we are on day 6 of Nodevember, and I know what you're thinking. I feel like a broken record. Today's November 5th. How could you be doing day 6 of Nodevember? Well, I'm staying a day ahead so that I can finally finish it. I've never finished a Nodevember, and after this, I don't know if I'm ever going to do it again after this month because I'm going hard. But before we get into the topic for today, let's go over what we did yesterday, which was feather. I made a nice render to depict this. So here we have the procedural feather. Actually, let me restart this bad boy in full screen. So here we have a procedural feather that I showed how to model. I then made a custom cloth solver. So this isn't using cloth solving. It's using a node-based one that I made specifically for this. I attached on the feather, which was the hardest part, and then I just resimulated over and over until I liked the motion, made it dramatic black and white, and that's what we did yesterday. You can watch that stream, and if you happen to be a CG Matter subscriber, what that means is you go to cgmatter.com. On the member site, if you go to the files for Nodevember, you can see I've now populated it. You click it, it will download, and you also have a link to the stream. So I'm putting all the project files up here, as well as, all the standard stuff. Okay? So that's the situation. And what I would also recommend, because it turns out some people are following along live, at least they said so last time, I'm going to be using some free nodes. So this is, you don't need to be a member for this. You can just go to my website, go to free nodes, download the add-on, and it will let you update. Speaking of which, I do need to update, and then I will talk about what the prompt for today is. So I'm going to open 5.0. I've heard through the grapevine that 5.0 official, not beta, is coming out in 6 days, November 11th, which is when I will start adding 5.0 specific nodes, because right now it would basically break compatibility. So there we go. I got my CG Matter nodes as a file path. And what this add-on does, at least what it does differently, is it lets you just re-download the updated version right into the same directory. So by default, it will let you choose a directory, but if you actually already have one, it will ignore this and just pick the same one. So I'm going to install /update, and now I have, in theory, the new nodes. Okay? And the way you check that is I always recommend refreshing the asset browser, but it might not be necessary. I know one of the new nodes I was talking about yesterday I wanted to implement was generated coordinates. I didn't have that until I updated it. So there you go. Okay, so we need to know what we're even doing. So day 6 of Nodevember, what is the topic? The topic is riveted, which, by the way, is misspelled. It's misspelled, Arendelle, unless it's like a British thing. I don't know. If you don't know what riveted is, I kind of had a sense, like I knew it had to do with connection or something, but I didn't really know what it meant. I gathered some reference. So here is like a riveted metal sheet. So you can see it's almost like we have all of these squares and they're connected. These things are called rivets, I believe. Here's another example. This one is all like squares and rectangles. This one has more interesting shapes, almost like a little sci-fi. This one also has more interesting shapes. So notice this L. And then here is a use case in real life where I'm seeing the rivets are either this or kind of like this screw looking thing, and they have various sizes. So it's kind of like connecting metal sheets together. So that's what we're doing. Now, I think for this one, it's actually very, very simple. At least I thought about it. I haven't tried it out. This approach, where we have only squares and rectangles and no special shapes, that we're going to do. If that goes well, I will consider the version that has more complicated shapes, which is a harder algorithm. Okay? So if you're following along, make sure to get the new nodes, and let us, without further ado, begin. So I'm going to save this as day 6. And by the way, while I'm doing this, let me shill a little. Nodevember day 6. Last live stream most people ever have joined. It was something like 6 people or something like that joined the website, so you know what I'm saying. Okay, so we have riveted. How do I plan to do this? What is my fancy schmancy algorithm? Well, I want you to imagine that I have this, so we're kind of doing it 2-dimensionally, and then we can consider 3-dimensionally, although that's harder. It is harder. But imagine we have a grid, something like a 3x3 grid, and more so, it's represented by like the points that make it up. So we have a point here, we have one here, we have one here. It's going to be like a 3x3. Okay? My algorithm is I'm going to start with the biggest face. So I guess right now it's 2x2, and I'm going to cut it somewhere randomly. So I could cut it here, I could cut it right in the middle horizontally, I could cut it here, vertical or horizontal in a different area. I will then randomly select one of these, and let's say I select the one on the left, and then I will cut it somewhere random. And this could have also been vertical. I'm going to cut it somewhere random. Then let's say I'm going for this one. I do it vertically. I'm going to select this one. I'm going to add a cut, 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 cut. So you can see how iteratively this will make the shape we need. And that's the simple algorithm I was thinking of. So really the only complicated part is how do we cut in a random way, and then also how do we do the rivets, which might be much harder. Okay, so that's the plan. I'm going to start off with a grid, as mentioned, and this is something I definitely want to do in wireframe, and I'm going to start off with a single face. The iteration, and when you hear iteration, you should think repeat zone, is select a random face. At least for now, I might change that selection later, and then run a cut operation. And that's it. You just do it over and over and over again. So first things first, so this is where we're going to do it. Let's make a little method, a little function, a little node group that cuts. So one obvious way to do it is, you make a slicing plane, like something like that, and that intersection is going to define the cut. In other words, using mesh Boolean and stuff like that. That's definitely the easiest approach. It might be glitchy and it might be slower, but it's definitely the better approach. It's like obvious. A slightly harder approach is suppose I want to do a cut right here. Well, there's no obvious way to do that, but what if I take this, I pin this side, and I scale it on the x-axis, right? So I'm going to scale by, let's say, 0.8. If I did that, now it's going to be a bit smaller. I then take this side and I extrude it by the difference, and that will effectively be a cut. But I want to start off with the Boolean method, and if that works, that's great. So I'm going to make a grid. This one I'm going to rotate in 3D space so that it is facing upwards. Okay, so we have this, and I want to cut one from the other. So I'm going to run a mesh Boolean. with this one, and let's see what that gives us. That gives us a cut, right? And then I can move it on the y-axis. I can also move it on the x-axis to get weird shapes. However, it would probably make more sense. Let me see. It would probably make more sense to just rotate this by 90 degrees if I wanted a vertical. And now you're starting to see part of the issue. It doesn't necessarily treat this the way I wanted it to, right? I wanted it to cut, but rather it only kept part of it. So that is something we need to solve. Okay? So let's say we have this one and we have a cutting plane. How do I get this to have an intersection? Well, what if I intersect? No. What if I union? Also no. Okay, so this is a case where it doesn't like it. However, difference gives us one side of it. What if I was to get the other side and then combine it? Well, how would I do that? Well, right now the face has an orientation. Let's say the normal's pointed this way, and that dictates how it's going to cut. If I was to flip it, I expect it to cut the other direction. So instead of 90, it's minus 90, something like that. So rotate like that, minus 90. Does it like that? Does it care about that? No. And then what if I was to flip our original plane? Will that affect anything? So we have this. I'm going to flip it upside down. And does it care about that? Or will it always choose the one on the right? I wonder. Flip faces. This is why I'm a little hesitant to use this method, the cutting method. Okay, I'm going to try one more thing, and then we'll have to get more creative. So here I have my grid. Here I have the cutting plane, and I want this to somehow do both. I wonder if I use the exact solver, if that's the way to go. Okay, so far that works, but it's glitchy. Why is it glitchy? Well, if we go over here, it seems to stop seeing it, but what if I make the plane bigger? It doesn't care about that, right? It's almost like cutting two thin things doesn't work for us. What if I bring it negative? Some of these. So that's looking a bit whack. What about intersect? What about union? Okay. And we'll see if this one respects flip faces or if it doesn't care. Aha! And now, interestingly, we have the opposite problem. So we either get to keep the right side or we get to keep the left side. What if I was to not rotate by 90 degrees? Well, now it's getting a little whack. So I get to cut, but only on one side, and if I flip faces, then we get the other side. So what that tells me we can do is we can just do both and join them together. And that will just work as kind of like we don't care about it. Okay, so I think that's what I'm going to do. So suppose I have a grid, and suppose I have this cutting plane, which I'm going to make a bit bigger than one, even though they're perfectly overlapping. This will just make sure that it cuts. I'm going to do it like this, and then I'm going to make the other version where I cut using flip faces. So this one is not going to use flip faces, and this one is. And this should give us both sides. Okay? I then join them together, and that almost gives me what I want. So now you can see I can cut up and down without thinking too much about it. I could even like rotate it. I can do whatever. But there's something subtle going on. And let me bring this to the top. So instead of this. Something subtle going on. We do have overlapping vertices. So we have 1, 2, 3, 4, 1, 2, 3, 4, yet we're supposed to have 6 here. So I'm going to merge by distance, and that's a good deal. Okay? So in other words, I have my thing that I'm cutting. In this case, it's a grid. I'm going to run 2 mesh booleans. one of which is going to use our cutting plane flipped, and one that is not. Okay, so this will always be our cutting plane because as we get smaller and smaller and iterate, this grid will always be bigger than the initial thing. It will always be bigger. But I do want control over, the slicing. In other words, I'm going to take all of this, I'm going to make it a node group, and we can call this like a single iteration or a single cut. Inside of here, I do want some custom control or some parameters to expose. That parameter, this we're never going to change. That parameter is basically this translation and the rotation. So let's make a parameter here, but then we also want the rotation. So it's kind of like we have two versions. We have one that exists like this, and then we have one that we rotate. So we have horizontal, we have vertical. And we kind of want a way to switch between these on the fly and randomly. Well, what if we add a switch geometry, where these are our two options, and we're going to make a parameter. It's either going to be horizontal or it's going to be vertical. Now, given that, it needs to translate either on the y or the x-axis, horizontally, vertically. Well, how do we do that? Well, in this case, I want to move along the y, and in this case, I want to move along the x. So you might be seeing where I'm going here. I can make a parameter that controls the y, and in this case, it will control the x. It's either that or have them exactly flipped. But you can see what I'm doing here. A single parameter lets us cut randomly. And there is a bit of a caveat here, and we'll talk about it. But not yet. Okay, so this y I'm going to call like the progress or something, or you could just call it the position or the slide maybe. And this can be our toggle. So let's see what that gives us. So here we have our slide that lets us cut this way or that way, and our toggle should have let us switch, but it didn't. And that concerns me. Why is that the case? Well, this is our cutting plane. It's because we never connected this. That's most likely why. Okay, so we have our cutting plane. It goes from 1 to -1 as expected, and now it goes vertically. Incredible. Now, this is fine, but each iteration I need to say, okay, now I'm picking this face, I'll cut it. And now let's go back to this face, and I can cut it this way. We need to say, what are we cutting each time? Now, why do I hesitate? Why do I hesitate? Well, for example, let's say we're cutting this square. Well, we can already do it horizontally, vertically by some slide. However, the slide goes from -1 to 1. So it's not guaranteed to hit this quad. So in other words, I've made a perfect cutter for the first case, but then it needs to be able to shrink and adjust, and it needs to know where can it go. So right now the bounds, I guess it's -0.5 to 0.5, and then same here, 0.5 to -0.5, but it needs to adapt, it needs to update. Well, this is where I'm going to use the normalize field node I've been raving about. So maybe these, I can clean up a little. Anything we know we're never going to touch, we can just kind of compress. And these I like to have in order. So top, bottom, merge by distance is always going to be the way it is. Group output. And all of this is fine too. So what I need to do is I need to find a way to take this slide, which can go from -0.5 to 0.5, but make it kind of a little custom. Well, this grid, or whatever it is we're feeding in, is going to have a maximum and a minimum x. Okay? Same thing with a maximum and minimum y. So one way I can do this is I can run a normalize field cgmatter.com, get that free node. And what I can do is I can take the position and I can separate by XYZ. And what this will give us now is it will give us a map where x doesn't go from negative 0.5 to 0.5, but rather it goes from 0 to 1. It will always normalize it, and that works for any size. And then this slide can now be a thing between 0 and 1, affecting this. So let's think about how to do that. Let us think about how to do that. So this goes from 0 to 1, but that needs to define this. So maybe like a map range situation. Or I could use the bounding box to literally get the minimum and maximum. I'm trying to think. So this gives us the 0 to 1. Maybe I do want, actually, now that I think about it. Do I want the bounding box? What we like about the bounding box is it will give us the minimum and maximum. So here's the grid. Here's the bounding box. We expect them to look basically the same. Okay. This gives us the minimum and maximum. I want to get those x and y values. And then our slide should always go between 0 and 1. But the subtype can be a factor. What that means is now we get this nice slider that should never go lower than 0 and never go higher than 1. So I like that. And I know this is simple, but it's harder to do live, I swear. Okay, so we have our slide. It goes from 0 to 1, and we want to map it to the minimum and the maximum. So I'm going to map range. So this is vaguely similar to the normalized field, but I was wrong. I think we need to expose some things to get it to work. So let's get the minimum, let's get the maximum, and we're going to take our slide that goes from 0 to 1 and map it from minimum to maximum. So what I'm thinking is we have some 0 to 1, and then it constrains itself to the range that it actually has to be within, if that makes any sense. And it does. Now, the difference here is one of them is going to be the x-axis, and one of them is going to be the y-axis. Okay, so there's going to be two versions of this. One version is going to be the x-axis, and then the other version, we're still feeding in our minimum and maximum positions. But now I want to reveal the y values. I take our slide, and we go from minimum to maximum, but in this case on the y. Okay? So we kind of have this symmetric situation. Maybe I do want to expose these a little, just so we can remember what the reasoning was. So we have one version like this. We have another version like this. One goes to the x, and then one goes to the y. And I think those are corresponding. It's either this or the exact opposite. Okay, so that goes here. That lets me transform the cutting plane that I can clean up here. And we have our nice bounding box. Okay. So this lets us transform the cutting plane that we can toggle between. Do I want the horizontal or vertical version? Then what's this one? This one's just a viewer node that I don't need. So that lets us toggle between the cutting plane, and then I do two versions of the cut, one with flip faces and one without. So that's our cut. I join them together, and we're gooch. And now really the way to test this is to see, does it indeed work as we do iterations, which we can test momentarily. So I actually am going to compress these. I'll remember. Oh, so symmetric. So beautiful. I've taken an appreciation to my my nicely ordered groups. So I take this, I join, I merge by distance, and I output that. Okay, so on the default case, it shouldn't really matter. Well, actually, this is a good example because it's supposed to go from negative 0.5 to 0.5, but now we can do this nice 0 to 1. And now we just got to set up the iteration, really. Please make a mermaid tail. I feel like you've asked that 1,000 times in the past. I might be forgetting. Okay. So now all we need to do is feed in the correct face. So right now the input, what does this input represent? This input represents the cutting plane, which will always be the same, so I can actually get rid of that and put that inside of here. So maybe I can call this cutting plane. That should never change. But what will change is what are we feeding in to be cut, right? What are we calculating the bounding box of? What are we transforming? Although this should also be the cutting plane. No. No. I got that all wrong. All wrong. So this is our cutting plane because that's what we're rotating and moving. But this is actually supposed to represent our input. What are we cutting, in other words? So I'm going to make that a input. That should also be what the bounding box is looking at. And now I think we're gooch. Maximum goochness. Okay, so we have that. We have that. And that is good to go. So this one, this input geometry is what are we going to cut? So maybe, I don't know, what should I call this? Like our surface or maybe our target. So this is our target for what we're going to cut. This will say horizontal or vertical, and this will say by how much. Okay? So in the case that what we're trying to cut is a grid, then we have that. In the case, and I might have not thought this through, but let's try a mesh circle. In the case that I have a mesh circle, I can do this. So this is actually a bisect node, interestingly enough. That's what we made. We made a bisect node. So maybe I can call this bisect. And that I should put out the node groups, the cgmatter.com node groups. Okay, so we basically made a bisect node. Great. And it would also work in 3 dimensions, I believe. So now, it's not necessarily the grid we're feeding in, it's just a face. So we start off with a grid. That grid I'm going to bisect. And that, what we're bisecting by should be kind of like a random number. So maybe the iteration could generate a random value, or actually it's going to be a single random value. This can be our seed. It goes from 0 to 1. And then we can also do, what can we do? We need a single random value for the vector. Or sorry, for the Boolean. I could try just reusing it, but that might create some kind of pattern unintentionally. So what I'm thinking is we have a random number 0 to 1, which controls the slide of the bisect. And this 0.5, is it greater than 0.5, decides is it a vertical or horizontal cut. Right? Now, the issue is if I was to keep doing this, it does do this correctly. However, it's cutting the same face over and over and over again. So what I need to do is I need to separate my target face and everything I want to keep. Okay? So I am going to take our geometry, and I'm going to separate by faces a random thing that I'm going to cut, and everything else that I'm just going to join together later. So the question is, what is it that gets cut? Well, it should be a random face. So I am going to, I have a node for this. It's like separate by index, which will let me separate a face by when the index is equal to something. Although I don't want just this as an output. I also want the opposite, like the selection and the inverse. So I'm just going to make a modified version of this, which maybe I should do later in the node pack. But I'm going to make a version like this that gets the same inputs. How am I? Oh, I skipped one. I'm like, these don't match up. And then it takes in the same menu. Oh, does it not like doing the same menu? Interesting. Well, what I was going to do is I was going to put in the inverse here. Okay, well, I'll add that later. So what I can do is I can separate by face where the index is equal to... Wait, do I have compare index? I do. I do have a node for this. So I want to check where the index is equal to a certain thing. So I made a node that just like, yeah, that just kind of does this for us quickly. And then the question is, how big can this number be? Well, I want a single random value, but it should be a integer. So maybe I should make a integer version. So I'm going to make a random value that's a integer. And that's going to be dependent on the iteration, and it can go from 0 to the maximum number of faces there are, which should also be the iteration, because every time we do it, we add a face. But the indexing starts at 0 for the iteration, so I'm going to run a increment. This just adds 1, like that. Okay, so let me explain what I'm thinking. We start off with a grid, and then for every iteration, I'm going to choose a random face. So this random face is going to be between 0 and the maximum number of faces there are. That way it can't choose a face that doesn't exist. And we add 1 because the iterations start at 0. And we want it to, first of all, have a single face. So when iterations 1, then we have 2 faces, 3 faces, etc. I check where's the index equal to this number, and for that, I'm going to separate the face. That face is going to get bisected using this like random like parameters, and then I'm going to join the thing that wasn't. We'll see if that makes sense, or if it does not. So at iteration 0, we have a grid. No, it is not working. And it's bringing in the cutter plane. Well, I know one thing we can do safely is we can take the number of faces. Although, wait a second. No, maybe it should be the actual iteration number. I'm just getting my like indexing confused. So, yeah, I think that's actually correct. Okay. Iteration 0, iteration 1, iteration 2, 3. So this is interesting. It actually... Okay, so you can see it's vaguely working. The only thing that gives me pause is why is this over here? And that is kind of like the mesh Boolean problem. And then sometimes it doesn't cut. Interesting. Well, let me separate these first of all, because they should be independent. So I'm going to generate a random Boolean based on... Or actually, I can generate a random integer that's either on and off, 0 or 1, based on the seed. So that's going to be our toggle. And what does it not like about that? Expects a single value. See, that's what I was thinking of here. So maybe let's make a single value where we increment, we increment the iteration so it doesn't give the exact same thing like it did before. And now we check, is it greater than 0.5? Like that. Okay. I think that's pretty good. So now the question is, why is it cutting so weirdly? So 1. And maybe this is a good time to expose the spreadsheet, see if there's any hidden stuff going on. So initially, there's one face with 4 vertices. Then there should be 2 faces with 1, 2, 3, 4, 5, 6 vertices, and then 7 edges. That's fine. Then we should have 3 faces with 1, 2, 3, 4, 1, 2, 3, 4, 8 vertices. So now it's somehow messing up. Could it be that I need to merge by distance here? It is. I need to merge by distance. Let's see if that was the issue. So that definitely is correct. However, now we're still getting these weird cuts. So I wonder, anybody have an insight in the chat? What I could do is maybe I could run these iterations and just kind of ignore the fact that it's not cutting correctly. And the way I would do that is I would delete geometry of the faces for anything where the normal is not facing upwards. Does that make sense? So I'm going to look at the dot product of 1, like that. And that will check as a -1. Interesting. So I want to delete geometry where it is equal to 1, 0. Okay, that definitely isolated it, but I feel like I'm not understanding. So I'm going to take the normal. I'm going to check where is it, and let's look at the face orientation. That might help. Where's face orientation? Okay, so these should all be pointing up. So I feel like I should take the dot product of this going upwards, and it's going to be equal to... It's going to be equal to 1 when they're aligned, I think. So I'm going to delete everything where it's not equal to 1. Okay, in other words, it's equal to 0. Maybe a safer way is I check where is it not equal to 1. And that should do it. So in this case, let's make sure. We have 1, 2, 3, 4, 5, 6, 7 faces. Great. And as I up the iteration number, okay, it's working. Again, the only thing that gives me pause is why were those booleans happening? Because ideally, I don't want to delete anything. And it's interesting that they always land in the middle. The cutter is being cut. Yes. So it's basically the logic over here. It's just like, what is the most stable version? I know one thing we can do is I believe these mesh booleans are designed to work with 3-dimensional things. Like the 2-dimensionality might create issues. So if for every single face, instead of treating it like a face, we treat it like a little box, that box is what gets cut, and then we just flatten it back down. That might add some stability. Worth trying. If not, we do have a temporary patch job. Well, let's see. So all I would need to do is I would take the input and I would solidify it. Okay? So I'm going to solidify it. And let's go back down some iterations to follow the logic. So we start off with a face. Then we go like this, which is getting cut. Perfect, just like before. But this time, we need to make sure that we do this and we flatten it back down. So maybe I transform this to scale it to the XY plane. So scale by 0. So now there's going to be even more overlapping, but we merged by distance. So in theory, it should be very similar, but maybe more stable. Are we using this delete? That seems much more stable. Now we're not even using this, and we're only getting the occasional glitch. Yeah, that's much more stable. I wonder what would happen if I change these Boolean cutters to float. I thought this would be the simple approach compared to the other algorithm. Maybe the other algorithm's easier. And I wonder now if instead of doing these two, I can just do a intersect. Yikes. Okay. Well, let's just go with what we know generally works, and then call the ones that don't. Okay, so we have this. The only thing I would like to optimize, and this is fine, and let's remind ourselves what it is we're trying to make, especially if somebody just hopped on the live stream. We're going for riveted. Specifically, we're going for something like this. And note that the spacing between these, or rather the size difference, isn't huge. Whereas in this case, it can get really, really granular. So what about instead of separating a random face, we always look for the one with the biggest area. That way, nothing gets too small. So what I'm saying is instead of separating a random face, I look for... Did I make a node group for this? I don't think I did. But we can look for the one with the maximum area. Well, how do we do that? Well, we look at area. We go to the field min-max. Or maybe I just do my normalize field. So now we're going to find the biggest face where the maximum is equal to 1. So in other words, I check where is the area equal to 1. Vaguely, and that should isolate the biggest face. I go like that. And I'm just going to save this off to the side. So now we're doing our selection differently. So we're looking at our face area for every single face. That should be correct. And we're looking for the biggest one. I wonder... Oh, shit. Whatever I just did was a mistake. Okay. It should find the biggest one, and it should separate. Why is that not the case? Interesting. I don't think there should be any difference between doing this and finding where the area is equal to the maximum. It is. But now it's not doing that many iterations. Nor is it finding the biggest one necessarily. Ah, face. Well, that was definitely part of it. Yeah. Okay, that looks like a much more even distribution. We can compare by going like this. Yeah, that's a much more even distribution. So all I changed is I said, look for which face is the biggest, and that's the one we should subdivide. And eventually, you get laggy, because what we're doing is we're doing a bunch of booleans. It does look like a CPU. Okay, might be a case to restart Blender. And then if we wanted to take it even further, if we want it to be super uniform, which I'm not convinced we do, I could look at the biggest face and I can look at what type of rectangle is it. Is it a vertical one? Is it a horizontal one? And that one can define which way it should cut. So that way it kind of prioritizes squares is a thing it can do. Okay. So what did we discover last time? We discovered... Oh no, where's the area equal to 1? Huh. Anyways, what we discovered is that we can use this field min-max idea. Check where this is equal to the maximum. Great. And then, like I said, what we could do is to choose this toggle. I can look at, is it more stretched or is it more squashed? Maybe is a good way to think about it. And that's quite easy to do, actually. So that's not even hard, because what I can do is I can look at the face and I can check, is it have a higher variance on the x or the y axis? So what I mean is I separate the face, and then before I choose my toggle, I need to do this function. So I can take the bounding box of this. I can subtract these. So this will tell me how long is it on the x or the y. I then want to compare x and y and check where's one greater than the other. So it's either going to be this or the exact opposite. So it's this and then less than. There you go. So this is one that will always cut in the wrong direction, okay? And this is one that will kind of prioritize evenness as compared to this one that creates longer rectangles, okay? Now, again, it's not going to be perfect, because what it's doing is it's letting the selection be all the way to one endpoint or the other, 0 to 1. And maybe that's the issue. Sometimes it gets too close. So to make this more stable, you could do 0.2 to 0.8. And you can see all of a sudden they're closer to squares. Or if I do it like 0.4 to 0.6, they're really becoming squares here. But I liked 0 to 1. Maybe let's add a bit of buffer, 0.1 to 0.9, just to avoid some of the issues we could run into. Okay? And now let's consolidate. So what do we got? We got this bad boy. What it does is it finds the face of maximum area and it separates it out. So that's a good little node group. Let me just kind of yoink. Okay. So that separates our selection from everything else. Okay, so that can be a node group. We can call this biggest face, or like select biggest face. And then the selection can be called biggest versus the not biggest. Great. Now the next priority is I want to do this check of which way it should be doing its toggle. So this is just one version of a way we could do this. We could have also done the random one, as we showed. So what this does is it finds, how would I call this? I would call it, so it takes in the biggest face. And what it does is it finds, is it stretched or squashed? So, like optimal direction, something like that. Like optimal in the sense that it maximizes the squareness. It like minimizes variation. So select biggest face, stretched or squashed. That's fine with me. It will then bisect the squashed one, join everything back together, and merge by distance, which makes sense. So how do I want to clean this up? Well, I can put the toggle at the top. That helps. And then I kind of want to flip these, I think. That will help it be cleaner. And now I could put the toggle back below. Okay, then we have our random slide. Those get joined and merged by distance. So this simple node group I can just call join. The top one is not the biggest, and the bottom is the bisected one. Not biggest, bisected. I can call this our joiner. And all of that gets fed in here. And this is basically our filter that avoids errors. Although in this case, we're not getting any errors anymore. Did we stabilize this? So let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's crank it. Ah, okay. So eventually we do get errors, but it seems somewhat unlikely. And I think the way I would do this is, remember I said it kind of handles 3D objects more easily. I would also make the cutting plane a 3D object and then merge them. But that might be more expensive. Although now it's got me thinking. It's got me thinking that we could take our cutting plane. So we already have a system that works. But it makes me think. If I solidify, and let me bring down the iterations just in case this blows up. If I take the cutting plane and I solidify it just by a tiny number, like 0.01, well, now it will create this spacing because the cutting plane is not being shown. That is weird. Are we using? Ah, it's because it's in a repeat zone. So the cutting plane is being solidified. And what that will do is it will create this separation. But if I want to avoid that, well, first of all, I'm going to make it tinier. Ah, but that becomes unstable. And then I was going to say, second of all, you merge by distance by like a bigger threshold. So it kind of finds its neighbors. But that overall seems like a less stable solution, it turns out. That's fine. I didn't want it anyways. And I wonder if the size of the extrusion matters. And I also wonder, so right now it's a plane or a face on the ground, the biggest one, and I extrude it. I wonder if lowering it as well, so it's centered on the XY plane instead of being on the XY plane, would add stability. So I'm going to take the strength, which was 0.1, and divide it by 2. This will mean it's centered, so you have to kind of visualize this. I'm going to bring this up, and that still created an issue. Did that add any stability? No, in fact, it reduced stability. Interesting. Okay. And I think the last thing I want to try is I never tried the manifold mode. Manifold is supposed to be the most stable. Did that help? Let's get rid of this. That was the way. We wanted to use manifold. Now we don't even need the cleanup process. Great. Thank you for popping in, Raphael. Okay, so we did that. Now, this wasn't even the point, if you remember. The point was to create rivets like this. But now I would do it on every face. And just out of interest, what would happen? So I can also expand it this way, and it will dynamically kind of fill that in. What would happen? Oh, boys. I can do it on a circle. I could do it on a triangle. A triangle. Interesting. Interesting. I might have to play with that later. That's very cool. Okay, so now we are doing the rivets. Rivet, which means I can take all of this and consolidate it. So this is going to be our cutter, which has a certain number of iterations. And then it just runs. It just calculates it. No, that's definitely cleaner. Okay, so this is our number of iterations. That was our input. And now we just got to create the rivets. And this is maybe the harder part. So here's what I'm thinking. Every single face is basically a rectangle or it's a face. I want to take it, so let's say I'm looking at this one, for example, and I want to somehow create evenly spaced dots, and they should be evenly spaced as compared to the other ones as well, slightly on the interior, okay? Well, how would I do that? Well, first of all, I need to treat every face individually. So if I go to my spreadsheet, you can see here are our stats. We have 11 faces, which is one more than the iteration because indexing. And I'm going to split edges. And you can see that changes the geometry. What it lets me do is now I can scale each of them towards their center. And then the idea is I now instance over these. So what happens if I do mesh to curve? You might be seeing where I'm going with this. Okay, so now we have 11 splines. And I resample them to have a certain number of rivets. Okay, so what I like about this approach is that it's evenly spaced, whereas, and let me just show you. I'm going to instance on points. Let's do a UV sphere. That's super tiny, even tinier. Okay, these are evenly spaced, whereas if I just use scale elements and then I subdivided, it wouldn't be even because it wouldn't look at the edge length. So these edges right here that are quite small will get super compressed. So that's why I like to use resample curve. So maybe each of them, well, even better, I don't want to resample because now it is also dependent on the overall arc path, which is better, but I want to space it depending on the length between the rivets. Rivet. So now this should be super uniform. Yeah. Okay, nice. And let's see if that's like a easy enough solution. I'm going to take this. I'm going to take my scale elements. I'm going to join them. Well, not the scale elements. I'm going to take the cutter output. What is going on here? I'm going to join them. And why is this? Oh, because I never scaled elements. And now these should all be on the interior. Now, you might be noticing it's not a perfect solution. Okay, and I'll show you why. If I scale this down, you're going to notice that, I don't know, this square pretty evenly distanced from its boundaries. Whereas with this rectangle, you have a spacing like this vertically. But horizontally, it's much, much worse. And the reason for that is that the scaling is uniform, which will kind of mess up things with big aspect ratios. So I kind of want to scale like additively, linearly. I want to consider the shape of it. So like we could take a single axis and, you know, just scale on the x depending on the length of it or the y. And that's using a pretty similar logic to what we did where we chose the toggle, right? We checked, is it horizontal? Is it vertical? So if I go into my stretched or squashed, we do the bounding box and, you know, we look at its x and y. I think I want to use that, but iterate on it a little. So I can move all this for now. I'm going to bring in our stretched or squashed, but I'm going to modify it a little. I don't need to know which is bigger than which. This will tell me its width and its height. And depending on its width and height, I can scale it by a certain amount. So let's say it has some width, and I want it to be a smaller width. So for example, I take the width and I subtract 0.05. So now the width is a bit smaller. The question is, to get this number, what do I need to scale by? So it's like we're taking a addition subtraction and we're turning it into a multiplication division. Okay? So if I scale by this much, what, you know, number is this? Well, it should be this divided by this. So we're turning it into a ratio. So these are very similar. What happens if I change this number? What's happening? I go like this on the x. This has some x width, which let me make sure it's the correct orientation. Maximum minus minimum. Because we're plugging nothing in. So I'm going to split edges. However, now we're kind of doing a bounding box on everything. So if I split edges and then, oh no, does that create, here, I'll go like this. Face orientation, where is it? So here we have 44 or 11 faces, and then with the bounding box, we should get 1, right? Because we need to treat these separately. We need to treat these separately. So how do we do that? Well, instead of the bounding box, we can look at its like min max, which is fine, right? Like I would take its position, I would separate by XYZ. For the X, I look at its, did I add a range node? I added a range node. So what this would do is it would basically take max minus min for the points, and it would output a range. Okay. Let's think about it that way. It outputs a range, and it outputs a range. So this is width and height, ideally. So let's say this is our width. I want to make it a tiny bit smaller, and I want to know its scaling factor. So I divide the smaller one by the original, and I make that the scale. Yeah, I think that did it. Well, we can find out. So I'm going to also subtract this by 0.05. I'm going to divide. So the idea is now it's considering the actual topology. It's looking at the actual shape of it. So this one's going to be on the y-axis by this number, and what we hope is as I look at this scale, which is really the separation from the boundary, they should scale more evenly than if I just scaled elements blindly. So this one's going to be uniform. So let's see. If I scale them uniformly, they go like that versus this. Is there any difference? I think a way to check is I compare it to the original. So you can see in this case, like in this rectangle here, right? So I scale it down. It has a much smaller vertical than a horizontal. Now the question is this version any better? No. It's not. Why is that? Well, we found the range. I subtracted a certain amount. So I'm saying I want to go from this range, this width, to a smaller width. And then I need to figure out the scale that will let me do that. Okay, so let's see. We have a width, and I want it to be a smaller width, and that is going to have a difference of x. But it would be on both sides. Okay. Of x. So it's going to have a difference of 2x. And what I want to do is I want to find their ratio. So if this is A and this is B, so line A is the shorter one, we know that A plus 2x is equal to B. And it's almost like we have this inverted because we want to subtract by a certain number, but that's fine. So we know that's equal to B, and I would imagine the scaling is going to be the ratio between them. So the ratio is equal to B divided by A, or is it A divided by B? Let's say it's A divided by B. So in other words, if A is smaller, like the result, then the ratio should be smaller. That makes sense. Well, what is A divided by B? That's B minus 2x divided by B. That is equal to 1 minus 2x over B. We're whipping out the math. So what I need to do is to get this to be similar, I take 1 minus this. And the fact that it's 2x is arbitrary, right? We can call 2x equal to y or whatever. So I'm just going to ignore the fact that there's a 2 there. Okay, so what does that tell me? That tells me that the scale should be 1 minus 2x over b. So let's say, you know, x or 2x or whatever is equal to 0.05. I divide it by b, which is the original length, in other words, the range, and I connect that here. And then similarly, I take this divided by the height, subtract. Okay, maybe. So what happens now? No, it still doesn't preserve the thing. Because it needs to look at the aspect ratio. Maybe that's what it is. So I'm going to take height divided by width. So that way it actually... here. Let me get rid of that. I'm going to take height divided by width, which is its aspect ratio, and it should scale differently depending on if it's the x or y. Let's see. So I'm going to multiply by this divide by that. I'm short-circuiting. I knew this would be the harder part. So this would give us the aspect ratio. I think the issue is when we take this thing, this calculation, which I think is correct, it's doing it such that it takes the field of everything. It doesn't look at each face individually. So it has this overall width and this overall height. So I think what I need to do is I need to split this. So I'm going to split two instances. And did anybody in the comments? Yeah, somebody just said it. So we split to instances based on the face, the index of the face. So now each one is its own face. Okay? We now do this like scaling nonsense, but for each face. Okay? So what does this give us? Okay, so now they're acting independently. They're acting independently. And now I can say for each instance, or actually I didn't even need a split to instances. I can go for each face. So now each face is going to be handled individually. I'm going to do this math. Don't even need to join it. Like that. So now they're all acting independently. Okay. And they care about this number. But it's very sensitive to it. And then I'm going to join it with our original. So this is just so we can look at the before and after. Okay. So it's set to 0. And then do I want to go negative? I'm going to take this and I'm going to divide it by like 100. The reason I'm doing that is I want this to be easier to play with. Okay. So each one's being scaled individually, but it's almost like they're doing it inverse of what they're supposed to. So maybe now I do that aspect ratio thing. I'm really not sure. Okay, so I take this. I'm going to multiply it by this number. No. I'm going to divide by that number. I do not know. I might want to like take this from first principles and just like think about it. No. Okay, let me think again. So for each face, which is now separated, for each face, what I'm going to do is I'm going to scale it on the x and the y. But it needs to be in a way that it's a constant factor. Okay? So a scale of 1 means I change nothing. So I need to nudge it a little. So it's slightly less than 1. Okay? So I created this, which is our input. I divided by 100 just so it's like easy to deal with. And then to figure out how much I should do it by, I looked at their x and their y. In other words, what is their width and their height? Okay? And then it's going to be 1 minus something that accounts for this. So if it's a bigger width, it should scale less. Right? So it's a divide. Okay. I feel that makes more sense. And then do I not want this? I think that's it. Woo! That is what is up, you motherfuckers. Okay, great, great. Okay, I just had to reason it out. So now it has constant spacing. That's got to be a node group. I want to see if anybody had that insight, okay? Because I wasn't reading. I'm not saying somebody didn't. Okay, what do we got? Pretty sure an offset static xy. Watching this while listening to Interstellar feels different. X divided by y times the scale factor. Is that what I did? I did. That's not what I did. Either way, we got it, okay? So that's what's up. That's all that matters at the end of the day. So we got this. Great. Let's consolidate it. I don't ever want to look at this again. But that's got to be, it's like a constant scale node group. That's got to be one. Okay. So I take this. For each of them, I divide. And the good thing is we didn't just get it. I feel like I understand why now. So this is going to be 1 minus the thing. And then I should probably be in full screen. So then we scale both of these on the x and y. So I'm going to call this scale x. I'm going to call this scale y. Those can just be stacked. Okay, and that's going to be by some value, which we're definitely going to make a parameter down the line. And that is what it is. And I'm going to keep this divide by 100 just so it's simpler, because this number is going to be tiny anyways, right? So I'm going to take this. I'm going to call this like kind of like a size-aware scale. So something like even scale, something like that. That's going to take a input, which is going to be scale. And then the question is, do we want to treat this as a positive or negative? So when it's 0, it's this, and as I increase it. So maybe I can call this even shrink in this case. Or I could just make it a negative so it's more intuitive, but that's fine. Okay. So I'm going to take the split edges, and I'm going to throw it inside of here. Although, did I ever need the split edges? No. Because now we did it by face. Hehehe. Incredible. It's incredible. Okay. So now, like, what was the point? The point is I can do the same logic we did before, where I take this mesh, I convert it into a curve. Each one of these is going to be resampled, not by the number of things, but by the length. Okay, so they're evenly spaced. And then on that, I can instance a rivet, represented by this. Yeah. Yeah, nice and evenly spaced. Now, the only question is this fine? Like, can they be misaligned? So here we have that misalignment. Here we have a bigger misalignment. If we wanted them to not be misaligned, we almost need to take, so let's say I have, you know, a bunch of points here. Each one's instancing a thing. I almost want to shift these points down, but along their path, which is going to be cyclic, by the way. Is there a node for this? It's something like redistribute. I mean, that definitely does something. So what does this do? Does it matter? I don't necessarily. Let's look at our reference. So in this case, it's lined up. I don't like that because that means I have a thing I need to do. In this case, it's kind of random. Well, I'm just not going to think about that. I'm happy to not think about that. So let's review. We have a cutter that will add these nice rivets. And more than that, it can have any, I mean, I know we could just totally do a Boolean at the end, but it works with any starter shape. Although, I guess one thing is, on these panels on the side, it like looks at that, but now the X, Y, I'm not going to think about it. So really what they should be doing is they should be looking at the center of their face and moving that much. I don't care. I don't care. How do you smart? I don't know. I'm just happy I got it. So now we have this, and then the question is, we have the system. We have the system. But how do I make it look good? Well, what I'm going to do is I'm going to extrude by just a little. And you can kind of see what I'm going for there. So I'm going to extrude individual by a random number. Okay? And I want to make sure that this random number is per face, right? I don't want some points to be higher than others. So let's just see if that's the case. If it isn't the case, I evaluate it on face. Nope, that means it's fine. So it knows to do that. Okay? And now the question is, you know, I do something like that. Let's make it a tiny bit smaller. And let's turn on cavity. We already have cavity. Shadow. Okay. How do the rivets know where to go? It's almost like they need to go upwards to match the thing. Upwards? Damn right they do. So for each rivet, right, and these are on the floor and they need to go higher, I'm just going to ray cast upwards and see what it hits. So I'm going to ray cast. I'm going to raycast onto our mesh. And then it's going to go to its hit position when it's pointed upwards. Okay? So let's move this over here. So before it instances, or we could do it after, but I'm going to move the points such that they go where they hit. Before, after. And that should be super stable. Like, I don't see why that would be an issue. And it isn't. Okay, so this moves the points. And then for sure, we want the offset scale to be a parameter, which it is. But, like, I don't want much variance. Otherwise, it doesn't really make sense how they're, like, riveted and attached. And I also want this shrink to be closer. Like that. And then the resampling, you know, should also be a parameter. Nice. Okay. Is there any way to visualize this better? Okay. Okay, so kind of like the last thing here, and this is looking pretty good, is I want these rivets to be more interesting. So if I zoom in here, they're kind of like these domes. If I look at this one, they're like a flat dome. If I look at this one's probably the best reference. So dome, and it punches in a little. We'll think about doing that. And there's some screws. I kind of like this idea of punching in a little, because then it really integrates it. And the way I would do that is I'd use a mesh boolean, but like, we haven't had much luck with those, have we? Well, let's say we do something like that. So I'm going to make it 16 by 8, so they're much lower resolution. And what I like about that is it will let me cut using booleans. So this is where I don't think manifold will work because, yeah. So we got to be careful about these super skinny ones. And to randomize this, I'm just going to take the iteration and I'm going to add. I'm going to integer math add. So every time we do this, we get a different generation. and that can be considered our seed. What was I saying? That can be considered our seed. That lets me randomize them, and then we can get to a point where if it gets too skinny, we can actually say skip that iteration, but nah. We just go for less iterations or something like that. So to get it to cut, we got to make sure this isn't hollow, but in fact, it uses my like solidify. So instead of extrude mesh, let's use the solidify. And I know I harp on this, but this is available at cgmatter.com. Go to free nodes. They're free. Just get them. Don't need to be a member. But if you want to be a member, you get so much. You get 5 years of project files, which is like 400 project files for $5. Some of them are quite complicated. And then we have the Nodevember. You know the deal. So instead of extrude, I'm going to do the exact same thing, but this time with my solidify. So now these should be like individual islands, but they're connected. They're connected because I merge by distance unbiasedly. Well, we can just kind of do the thing we did before, where we do a for each. So that lets me treat them separately. So this is a good trick to not use instances, although I'm sure it's fine to use instances. So I'm going to solidify extrude every single face in here by a random number, where the seed, how tall is it, is dependent on the index, and that goes here. So now these should be solid, and like I was trying to do, they should be separate. Yes. Okay. Okay, so let's make this a nice node group. This one's going to be called, like, solidify. I know the other one's called solidify, but who cares? So this is our solidify. I want to make sure that I have my maximum height. I can call this random max. Okay, and the whole reason I solidified it, if you remember, is we had these and I wanted to do a Boolean, which wouldn't work otherwise. So now we have this, we have that, and what we hope is that we can cut one from another. And we'll see if that's the case. So I'm going to mesh Boolean. We actually want this to be our original mesh. And we subtract away, and I'm going to make this super low resolution just in case. We subtract away this, and that kind of works for some of them. What if I do exact? It definitely doesn't like that. So exact, not so exact. What about hole tolerant and like self-intersection and all that? We'll see. No. We'll use float, and I believe manifold doesn't. I didn't expect that to work. Oh. Okay, so you might be wondering, why do only some of them get it, by the way? It's because we have our curves that are sitting on the floor. Now our solidify, which is 3D, also has a floor, so some of them might hit, you know. So what I would do is I'd go to my raycast and I would set the source position, where do they start and then where do they shoot, to just do a tiny bit of an offset, like 0.001. And just with that change, haha. And what we like about mesh Boolean manifold is it's so much faster. So, for example, let's say I was to run my shrink. This is real time, okay? That's why I like it. Okay, and eventually we might change it from a sphere. Okay, so that was the idea there. So now we cut it away, and then, by the way, this is a shadow artifact, if you're wondering. And then what I was going to do is I take this, and I join them together with the instances, but I scale them down a little, like 0.9. That way they look like they're actually in there, right? And this idea will work with any shape, So let's take our UV sphere. What was this again? I don't need it. I'm going to take our UV sphere, which I'll make full scale, and I'll make this a bit more interesting. I'm going to do that by, first of all, upping the resolution. And I kind of want these thin domes. Okay, easy enough. I'm going to transform and scale. And then I might want to... I mean, there's no reason this shouldn't work, right? The only thing is I want to make sure before I plug this in is I'm going to set my scale to like 0.001. I forget what it was. Maybe it was like 0.01 because the sphere is now of radius 1. That's going to be our instance. Is that correct? No, that's too big. There we go. And now these still have their cutouts. Of course, it's a little slow, and we want to reduce this as much as we're willing to get a faster cut. Set shade smooth. That's riveted. Now you could add a bit of variation so that it's not perfect, but maybe the perfection is what makes it look interesting, right? I think we can even optimize this more. So if you think about it, this bottom here isn't really contributing much to the cut, or you don't even see it. So maybe what I want to do is I want to save on some geometry, and I'm going to cut relative to a grid, a bigger grid, like this. It did not care about that. Okay, so we have this, we have this. It didn't care because exact. Almost. I never know what these do, but clearly that helped. And then this is set shade smooth. So for reference, we went from 320 faces to 181. And I imagine that this will be faster. But now mesh boolean's not working because it's not manifold, right? Is that what it's saying? It's not manifold. What would make it manifold? Is it the triangulate? No. Is it the merge by distance? No. Let's see. So for this to be manifold, I think what it means is it's facing the wrong direction, if I had to guess. No, that's fine. And really, I'm kind of surprised that triangulate wouldn't help. Very surprised, actually. How do we do this nicer? Maybe we do that thing where we stop like treating it as a flat object and actually solidify it. Maybe that will help. Okay. So like ultimately I feel like this should be the same thing, but it like that for some reason. Always Boolean in 3 dimensions. I feel like that's the lesson I learned from this tutorial live stream. Okay, so this, it's not that interesting. It's just making the flat sphere. And then I shade smooth. Okay. This is what I instance. So maybe this can be our single rivet. Okay, that's instance, that's realized, and it's not lost on me that if we have instances, we can actually do more interesting things. Like, for example, what if I take the scale and I randomize it? So instead of 0.005, it's randomized from a range. Okay, so now we have the randomization, and it still does that cut, in theory. Excuse me. At least for the big ones. So let's do 0.003. Yeah, I think it's definitely doing the cuts. It's just that in this case, it's not really visible. No, it's not. It's literally not doing the cuts sometimes. Why would it not be doing the cuts some of the time? So if I set this to just the sphere, it likes that, but it doesn't like the flat because we move it down a little, right? Minus 0.001. There we go. Z fighting. What are you can't live with it? You can't. I mean, I can't say you can't live without it. I would be happy to live without it. Okay. There we go. So now maybe, see, I think the risk we run is if I make it too small, like we then need to move it further down. Oh no, I like that. So now if we join them together, each one's going to be riveted, but they're not all necessarily the same scale. Now, do I want that? Yeah, but barely. And then you can also add some messiness where they, translate inwards. They rotate. You can kind of tell they're not in there. Okay, just shifting that down a little. That does sacrifice some of the savings we had. So here we have 181. Yeah, it adds like 20 faces, which when you multiply it a lot does actually end up mattering, but okay, there we go. So we got this rivet. This can all be consolidated. Let's think. So we have this. That's our instance. I set position. Okay. So we have our shrinking. I'm going to convert it to a curve and resample. That is going to get set position via array cast. so that this can all be a node group. And let's see. So this is going to be our cutter that we shrink. This is going to be our solidified version. So I can call this solidify panels. And then this, so this is our panels. What is this? This is kind of like our instancing thing that ends up being important. So maybe this can be our, it can be our, like, is cutter correct? Shrinked. Shrunk. I'm just going to call it shrink. I don't want to use the English language fancily here. And then what is this? This is going to be our spawning points. So I can call that points. And then this can be, what is this? This is our solidify panel, which we don't even need. I don't know why that's there. So this shouldn't be any different. Oh, wait. I know why that's there. It's because of the... Okay, yeah, it's because of the ray cast, but it doesn't need to be outputted. That's for sure. And then I want to make sure the length is an attribute, so that's the spacing. And I think that is about it. So this length is probably more accurate to call it spacing in this use case. This can be called our panels. This is never going to change. Never say never, though. Okay. Oh, that's annoying. Oh, no. You can make them the same size. Okay. So this is our, like, spawn. What about create spawners? Because it doesn't yet instance anything. It just lays the groundwork for where it will be instanced. And then we have our rivet. We instance on points with a random scale. We realize, we scale, and then we join. How do I want to do this? Okay, so this, it's almost like I don't, Okay, let me think about this. I think this is a node group. What it does is we want this realize instances inside of here. Whoops. And then I do want my rivet exposed so I can easily change that. Okay, let's name it. So we got our points, we have our rivet, points, rivet. By the way, I would love it if when you type like blah, 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 and you hit tab, it goes one down instead of going to the description. That's how some of this stuff actually works. Like when you do a menu switch, for example, right? If I control click, I can type, I can hit tab, type again. I would love that, personally. Okay. So what does it output? It outputs our rivet geometry and our rivets. So rivet geometry, and then also just the rivet instances. That's used for a different purpose. So create spawners, spawn rivets. Can't help thinking about frogs every time I say that. Okay, we got our Boolean. We got our join. Okay. I think we're golden. How long have we been going? Almost 2 hours. Okay. I won't do the second algorithm, but I will talk about what I was thinking so that you can try to implement it yourself. Because I think this is plenty cool. It was cooler than I thought it would turn out, actually. Okay. So let's review what we have. We have, let's just kind of do it like this. Okay. So what is the situation? I'm just trying to look for something that easily visual, you know what I mean. Whatever, that's fine. Okay, so we start with a shape. This case, it's a grid. It could be literally anything, turns out. I cut it into a bunch of pieces that can be iterated upon and randomized. For that, I create solidified panels that actually have like three-dimensional geometry. And then I also take these panels and in the longest part of this live stream, figure out how to scale them inwards. So that's our shrink. From these, I can create spawners that have a certain spacing, and I spawn the rivets. So this is what the spacing looks like. I use the rivet geometry to cut it out. I also make a rivet version. And that way I join them, but they have that little hole in it. So that's kind of the whole workflow. And then, there's materials and whatever else. So I want to talk about the other algorithm. And again, remember that this won't work perfectly. Sheesh. Is it too big? Didn't like that, Geo. But a lot of this, rather, will work with any input geometry. So there's a case. I think we just want less iterations. So it kind of, sort of works with any geometry, and that looks cool in its own right. What about a star? Okay, that's way too big. Let's go 0.5 by 1. So there's some glitchiness to figure out. I assume it's because of the manifold Boolean. But let me talk about the second algorithm. So the second algorithm is how do we take something like this, which is what we made, right? Just dividing squares, parallelograms, rectangles. How do we take that and turn it into this? So you might be wondering, what's the difference other than the material? The difference is you can see these kind of L's. Here's another one. They're not perfectly standard shapes, whereas this one is all rectangles. The algorithm, in a way, is quite similar. Kind of. Not really. So assume we have a grid. What we did last time is we picked vertical or horizontal. I'm going to go vertical, and I pick a position. I then take the biggest one. I'm like, okay, horizontal. Take the biggest one, vertical. Take the biggest one, horizontal. Vertical, horizontal. This algorithm that we just did could not generate those L's. Couldn't generate those L's. So what can generate those L's? Well, what if we take the grid and instead of treating it as a thing to cut, we treat it as a grid that actually represents like a grid of points. So let me make a basic one. Let's do 1, 2, 3. 1, 2, 3. 1, 2, 3. And each of these isn't just a point, but it represents a potential quad. Okay, so this is a 3 by 3 grid. What you would do is you would start by choosing a point. So let's say I choose this one. When I choose a point, it means I create a square. Okay? Now, I have an option of growing it or not. I'm going to decide to stop. Okay? The moment I do that, this no longer is editable. We have that square. Now I pick a new point. So let's say I pick this one, which automatically generates that quad. I have a choice of do I want to stop or do I want to grow? Well, let's say I do want to grow. What that will do is it will look at its neighbors. So by the way, this grid's connected by edges. So it will look at its neighbors, which in this case is these two, and it will ask, do you want to grow or do you want to stop? I'm going to say stop. So in that case, it would generate this piece. Really, it's like this, if you think about it, but that's our piece. We then pick a random point, like this one. Do I want to grow or do I want to stop? I'm going to choose stop. And again, these points are out of the running, so they can't be used to choose. Next point, I'm going to choose this one. Or maybe, yeah, I'll choose this one. Do I want to grow or not? I'm going to choose grow. It's connected to these two. Or you could treat it like there's diagonal connections. So let's treat it like there's only like, you know, basic up, down, left, right connections. Well, I'm going to choose to grow. So now this one, and this one all belong in the same. And then I can say, do I stop or do I choose to grow? I choose to grow. So it looks at its neighbors. And now we've said that this piece is a single piece. Now remember, really it's something like this, but we know that was all in one iteration. So that creates this L shape. And you do this on a very dense grid, so not 3 by 3, but like, you know, I don't know, 10 by 10, and that will create interesting shapes. It can even create, I don't know if I have the example here, this one. It can even create shapes like this that are super weird. It's kind of like a flood fill. So that's what I'm thinking for the algorithm. Let me read the chat. Okay. Couldn't you generate a normal map where rivets meet the surface? Yes. What I would do is I'd even take it a step further. I would keep the rivet geometry because I do want it to be there. Like what if I look up close? I want to see that there's actually something there. But I would look at an ambient occlusion map, which will tell me where the rivet's touching the thing. And for that one, I would use it for shading. You ever messed much with rigid body solvers and geonodes? Yes. Look at tutorial live stream number 3, I believe. So number 3 was this ice render, and the way I generated it is I made a bunch of ice sheets and I used the geonodes rigid body solver to have them not overlap but rather stack. Okay? Let's get infinite spaceship hulls at the push of a button. If a rivet mesh and the whole mesh would be one instant object instead of cutting each hole at the location each rivet is placed, would that make a difference in optimization? I think what this person is saying, do you treat the rivets as 100 objects or 1? We treated it as 1 object. Okay? And I think because that worked with manifold, I think that's much faster than iterating through them, if that's what you mean. What just randomize on positive scales? I assume you're talking about these complicated shapes where you just like, you essentially create random Manhattan selections, I don't think that's how I would want to do it. But just to entertain the idea, let's see what that would look like. So I don't know if this is what you meant, but this is what I'm going to do. So I'm going to make this one over here. I'm going to make a dense-ish grid. So let's go 10 by 10. Whoops. Let's go 15 by 15. On this, I want to separate it into chunks. And like one simple way to do that is take a Voronoi texture. Okay, what do I mean? A Voronoi texture, if I look at this color, will, if I set this to faces, it will be more obvious. It will generate these chunks. And because of how Voronoi works, those chunks will be near each other. However, by default, this doesn't look too good. So what I would do instead, you can almost see the Voronoi pattern, is you would take Euclidean and you turn it into Manhattan. What Manhattan does is it calculates distance differently. It looks up, down, left, and right instead of using diagonals, in a sense. Here you have that Chebyshev is a way to do it. Minkowski. It's not a bad way to do it. The only thing is now we do that shrinking operation, which is fine, but it assumes certain things like that they're rectangles or whatever. But we'd need to deal with that anyways. You could even up the detail and the roughness, but then you get like individual tiles. So look at this. The randomness might help you get stability. So here we have kind of square tiles. Here we have random, but halfway through, you get tiles that neatly touch each other. Okay? So if I was to take this grid and I would split edges, which what that would do is it would treat these as individual elements. I would split edges, but not everywhere, just a certain selection. I would take this color and I do, it's something like boundaries, edges, face group, what is this? Face group ID to boundary edges. I would connect that, I believe. Yeah. And I would make sure that this outputs a random number. I'll explain what I'm doing in a second. Actually, let's use the hash. The hash can take in a color and output a number. So I would do something like this, I think is what the person is saying. Okay. What I did here is Voronoi outputs these like cells, which are useless to me because I need to know the ID. So like one chunk, one panel is called panel 1, one's called panel 2, one's called panel 3. The color kind of gives us that. So we have the red panel, the blue panel, but it's not easy to work with that. So what you do is you have this hash value that turns it into like number 1, number 2, but these are huge numbers. This face group boundary finds those boundaries. Let's see if I can visualize this. Edges, faces, points. Not the best way to show it, but it will find like the separating lines. So maybe a better way to show it is I'm going to separate edges by this. So it generates this map. Good way to make mazes as well. And then, you know, you split it, yada, yada. Okay. So that's definitely an idea. Let's see if we have any other brilliant insights. Let's see. That was a good question, though, or a good remark. Okay. So as you may know, if you've been watching these live streams, is that I always take a question at the end. I only take one, okay? So this is your chance. I'm going to like wait like a minute for all these questions to come in because I'm 30 seconds ahead of you in time. You are living in the past while I'm living in the future, present. I only answer one, and I ideally answer either a technical question or an interesting question. So I'm going to let that take a moment to populate. And for the last time, I do want to say that all the free nodes that I used are going to be on cgmatter.com. Pick up the free nodes, which I'm going to, every time I do one of these live streams, I'm like, oh, that should have been a node. On this website, which that's there, there's also another free section is I have a blog that I post very infrequently to, but they're interesting reads, I think. And then also the shilling is there's a member site. So this is $5 per month, so however long you want to be there. That has all the files. So you remember 2 tutorials ago I did curl fields. So in here you could get the project file. So if I click this, it downloads that. And there's just some remarks. And additionally, relevant to this, you get the Nodevember thing. So like later today or tomorrow, I'm going to upload day 6. Yeah, day 6. And there's the archive. Okay? So I just want to show that. I'm going to give this a moment more for people to ask questions. And I can see that during this live stream, 1 new member joined. Usually it's after. So I'm not going to give the name, but Nick, if you're here, I see you. So I would highly recommend that. I mean, of course, because I run it, but I also think it's a good service. And now let me answer the question of today's live stream. Okay, what do we got? I'll open these up here. Okay, the alignment's different. Where was I? Okay, here we go. What's the worst color and why? Let's go out today and answer 2 questions. No, that makes it less special. What's your goal with giving out these free notes to everybody? Do you still have the red top you bought from Mass in 7 series and has it been washed? Any plans to make GeoNodes point cloud to mesh tutorial? I did do that. I did a tutorial on that. I don't remember what it's called. It might be, like, look up Delani triangulation. And where do you do traditional? Okay. So, there are, like, 2 questions. I only want to answer one, but the 2 that are on my mind is, do I have the red top from the Mass in 7 series? And do I have, what is it? Why do I do the free nodes? So I'm going to answer the free nodes in detail, but as for the yes or no question, yes, I think. I might not. But go watch the Mass in 7. I might have hit it, but it might be there. Okay, so to answer the question, what is your goal with giving out these free nodes to everybody? So I would say it's threefold. 1, it's just a nice thing to do, which feels good. And it's of value. 2, it lets me record tutorials, or in this case, the live streams, in a way that don't take as long. So anytime I want to distort coordinates, I don't want to talk about it. Like, I'm done. It's over. Or solidify. It lets me go faster in the tutorials and make it more interesting. And I don't like explaining those things at this point. And then third of all is the way to get those free nodes is you have to go to my website. And then you get the add-on, and then you can auto-update forever. But you have to go to my website, and of course the goal there is I want to get members on the site, which is impossible unless you go to the site. So 1, it's a nice thing to do. 2, it makes the tutorials more interesting or faster, and it lets you focus on the thing. And 3, it's a way to get people to the website. Okay? So that's your answer. So thank you, everybody, for watching. Again, cgmatter.com. Get the free nodes, and then also become a member. I'd recommend it. Like, all this Nodevember stuff. Come on, it's so tempting. Tomorrow, we are going to do... Let me just make sure that I know what it is. Tomorrow we are going to do, I don't even know what it is. We're going to do Precious. And I swear I'm not going to do Lord of the Rings. I want to be original. I want to be original. So I'll figure out what that means for me. And yeah, join me tomorrow. There's no time of day. It's just whenever I'm awake and want to do it. So I'm just going to drop in my website. And thank you, everybody, for watching.